Good morning, everyone. Last time we talked about applications and processing of metal alloys uh, for the first part about steels. And today we are going to continue our talk, but now this time we are going to talk about the cast iron. And so here are the objectives, and we want to learn the cast irons. We want to learn the non-ferrous metals, and we want to learn the commonly used fabrication approaches um, for metals. So remember, this is the classification, this diagram I showed you last time. And so here is the metal alloys. We have ferrous and we have non-ferrous. Ferrous means that so this material contains the iron. And so we talk about these ferrous, we talk about steel, we talk about all these um, the steels last time, and today we are going to focus on this cast iron, and which cast irons, which include the gray iron, the ductile, this is the nodular iron, the white iron, malleable iron, and compacted graphite iron. So ferrous alloy, iron-based, and this iron-based, I told you already, steel, cast iron. So for nomenclature for steels, and we have ASI or, and this is and not or, ASAE, Society of Automobile Engineering. And so you need to know that, okay, what this is a two cross sign stands for. It stands for the weight percentage of carbon if you multiply by 100. And for example, for this 1016 steel, it means that so for this steel, the carbon um, composition is 0.60, 0.6 percent. And stainless steel, we also need to have 11% chromium at least. And here is the cast iron. So ferrous um, alloys with uh, if the carbon composition is greater than 2.1 weight percent. More commonly, it is 3 to 4.5 weight percent of carbon iron, and we call this the carbon composition we call cast irons. And cast irons irons have low melting temperature, relatively easy to cast. Okay. Also, generally, it's very brittle. So previously, many households use the cast iron utensils, the pots, but now we changed. We have changed to start using this is stainless steel. Um, the cementite for this is the cementite decomposes into the ferrite and graphite, and so this is cementite Fe3C and some condition high temperature, and we will have 3Fe plus this is one this carbon this the atom, so this graphite. So generally this is a slow process, and for this is decomposition. So let's come back to our phase diagram, iron and carbon true equilibrium diagram. So here is austenite. We know that, right? So with austenite, this is a ferrite plus austenite, and this is a ferrite plus this graphite, and plus this cementite. Okay, so this is plus this cementite. Um, so this we call this graphite. This graphite formation promoted by silicon. If we have 1% of with percent of silicon, and we can promote the graphite formation. And also this slow cooling can promote this is graphite formation. So here's the types of cast iron. And so first we talk about green iron. And green iron is the carbon composition is from 2.5 to 4.0 weight percent. And so this is this kind of green iron, and they have the following characteristics. And they have graphite flakes and graphite flakes, weak and brittle in tension, stronger in compression, and they have excellent vibrational dampening because the more carbon inside. And also the wear resistant. They are wear resistant. So this is the microstructure of green iron. So next one is the ductile iron. And ductile iron, you can see when we compare these two micrographs, we can see the distinct differences between them. And so ductile iron, and when we add this manganese, or this is Ce, the graphite as nodulus, not flakes. This is a nodulus. So you can see this is a circle, sphere, not the flakes. The matrix often pearlite. This matrix often is pearlite, which is stronger but less ductile. So this is the characteristics of ductile iron. And so next one is white iron. And white iron has 1% of weight percentage of silicon. And so this one. And it is a combination of pearlite and this cementite, and very, very hard and brittle. So this is a micrograph. For malleable, another cast iron we call malleable iron, and heat treat well, heat treat white iron at this 800 to 900 degrees C, and graphite in rosettes, reasonably strong and ductile. So this malleable iron, and as the name suggests, malleable iron, and it can be shape can be changed, and that means it is ductile. And so last one is compacted graphite iron, and so this relatively high thermal conductivity. So good resistance to thermal shock, also because of the high composition of carbon, and low oxidation at elevated temperature. So this is also is a very, very beautiful um, the characteristic that many engineering applications value. Then we talk about the production of cast iron. So here you can see this is usually our cast iron commercial, the cast iron range for here to here. So this vertical line is a cementite. Uh, you can see, okay, the reheat and hold at 700 degrees C for 30 plus hours, and fast cooling. Then we fast cooling, and another one is slow cooling. Fast cooling we get pearlite plus graphite. Slow cooling we get ferrite plus graphite. You can see pearlite malleable and ferrite malleable. Uh, and so here, so this is the fast cool from here. Fast cool, moderate, and slow cool, and we can get white cast iron, pearlite green cast iron, along with this ferritic and green cast iron. If we add this is manganese and Se, and for moderate cooling, we have pearlite plus this graphite. Uh, uh, this is slow cooling. We have alpha plus graphite. Um, uh, this is a GN graphite here. So this is applied ductile cast iron. So the ferritic ductile cast iron. So limitations of ferrous alloys. So they have relatively, even though ferrous alloys have been commonly used for many engineering applications, but they have some limitations, um, disadvantages. And first one is relatively high density. And so because of this reason, and a lot of aerospace related missions and engineering applications do not use ferrous alloys. The second, relatively low electrical conductivities and low electrical conductivities. And third one is generally poor corrosion resistance. And we can see, especially for cast iron, we do not have any coatings on it. And so we can see the cast iron, and they usually are very, very easy to be corroded. Then we talk about non-ferrous alloys. Okay, so these non-ferrous alloy include all these alloys that do not have any iron inside. And so this is a non-ferrous alloy. Okay, this is a non-ferrous alloy. First one is a copper alloys. This is a very commonly used. For example, brass, bronze, and this is COB. For brass, xenon is a substitutional impurity, and costume, for example, costume jewelry, coils, and corrosion resistant. So bronze, and we have SN, aluminum, silicon, uh, nickel are substitutive impurities, and this for bushing and landing gear. So it's for bronze. And for COBE, and precipitation hardened on four strands. And you can recall, and precipitation hardening is one of the four strengthening mechanisms that we have talked about. And you can just recall what other three strengthening mechanisms are. So second one is titanium alloy. This is another big category that is non-ferrous and relatively low density, and versus 70.9 for steel. You can see it is much lower and reactive at high temperature, and space applications for titanium alloys. Also, for a lot of um, bio-related applications. So another one is aluminum alloys, and we all which are also widely used. Low, even have lower the density. Uh, we can add copper, manganese, magnesium, silicon, manganese, zinc additions, and solid solution or precipitation strengthened. And this is solid solution precipitation strengthened, and structural aircraft parts, and this is a packaging. So for aluminum we use a lot of aluminum alloys in our daily life. Uh, Next one is magnesium alloys. Very low, you can see lower, ignite easily, aircraft and missiles. Then refractory metals. Refractory, as the name suggests, it has very high melting temperature. So this is a high melting temperature. For example, neodymium, molybdenum, tungsten, and tantalum. So last category is the noble metals. Uh, this is silver, gold, and this is a PT, and they are oxidation and corrosion resistant. Any questions regarding these commonly used non-ferrous alloys? No? Okay, we talk about this one. Metal fabrication. And how do we fabricate metals? We know these metals. How can we fabricate? And how do we fabricate? And blacksmiths, and just like many years ago, um, people use hammers. These are called forged, and cast the molten metal into mold. We melt elevated temperature and melt the metal alloys, and then pour this is a molten metal into a desired mold, and then after many hours of the cooling, we can get what we wanted. And forming operations, and the rough stock formed to final shapes. Then we talk about hot working versus the cold working. And hot working, we have deformation temperature high enough for recrystallization. So this includes large deformations. So this is hot temperature. And for cold working, usually the operating temperature is much lower than the recrystallization temperature. For example, string hardening will occur, and usually this is a small deformation. But I would say this is just comparably. Okay, so this is large deformation, and cold working, I would say from another perspective, I would say this one is always also this large deformation. This is smaller and this is larger. So this is just the comparison of these two guys in terms of the size of the deformation. Then we can metal fabrication methods. Forming. So this is the hammering, the stamping, wrenches, and these are craft shops force. This blank is a workpiece, and so this is we apply the force here, and so we can have this our final shape. This is rolling. These are two rolls, and so here is the workpiece. We just put there, and then out these two rows compress it, and we have a thinner workpiece. So drawing is also very similar to this one. This is the two dies here, and with this material, we have very high tensile force to pull this metal and through this orifice or through this is orifice, and then get this desired this is a cross sectional area. And then extrusion. Extrusion, this billet. Billet is also the raw material. And we can just die. Here's this container. So here's a die. This is a force here. This is a ram. And you push it. And then you can just like we push something very soft using our hands. And this is orifice and this extrusion. A second category is a casting. The casting mold is filled with molten metal. The metal melted in furnace, maybe alloying elements added, then cast in a mold. The common and expensive. The many years ago, people use this one a lot. This gives good production of shapes and weaker products, internal defects. Um, Good option for brittle materials. So this is casting. For the engine, okay, so for big engine, if you have been working, have this co-op or this internship in a big assembly, the machinery fabricating industry, and you will see the engine, the big engine, usually they are the casting, they are made using casting. So casting, uh, so this is investment casting, low volume, complex shapes, for example, jewelry, turbine blades. So stage one, so this is stage one here, and put wax, right? So it's wax, mold formed by pouring plastic or Paris around the wax pattern, and plaster allowed to harden. So this is allowed to harden. So wax is melted and then poured from mold, and hollow mold cavity remains. So stage three, molten metal is poured into mold and allowed to solidify. The die casting, uh, the high volume for alloys having low melting temperature. So this is the first one. Then this continuous casting here. As you can see, a simple shape it goes down, molten, it solidifies, and continuously. And so this is rectangular slabs or these cylinders. And also another category is, um, for example, is a miscellaneous one. We have powder metallurgy, the metals with low this ductility, right? So this we heat it, so we compress it. So this one we densify. We have this kind of material. This is a point contact allowed temperature, low at low temperature. So this is densification by diffusion at high temperature. And so welding. Welding is very commonly used manufacturing method for large assembly, large machinery, the building industry. For example, the ship building or vehicle, the building industry. Welding, when fabrication of one large part is impractical. Uh, so here, so this is a piece one and piece two, and without loss of generality, we just assume these two pieces they are different materials. So we just use this is heat, very high temperature, and this melt. So this is these two areas, this area, and which covers piece one, part of piece one, and part of piece two, and then we have some filler metal also melted, and so this is a base metal, melted, and then fuse the base metal when this molten material solidifies. So this area, because the temperature, the heat reaches this area, and we call heat affected zone, regions in which the microstructure has been changed. This is a heat affected zone. And for here, this one is unaffected zone. So for welding industry, for welding, for welding, and we need to pay attention to the structural integrity in this area, especially in this heat affected zone, because there might have some defects there, some pores and some disease impurities. Um, all these can reduce the structural integrity, structural strength of this area substantially. And be very, very careful. Okay, that's all for today.